Hi everyone, we're going to be looking at a two-part series here on graphs, the first one being qualitative graphs. So those are graphs without numbers. Let's get to it here. In AP, what we're going to be looking for is really two different things. One where we're asked to create the graph or sketch it, and the other one where we're given the graph and then asked to analyze it. For example, then describe the motion. So we're going to look at both of these examples, but the general idea with APC is they want you to be able to connect each of these representations to each other. If you're given one, you should be able to produce other ones. So for our focus here on qualitative graphs, given any of these other representations, we should be able to generate a sketch of a graph. If you're given a sketch of a graph, you should be able to generate these other things, which most relevant is the written descriptions. So let's look at sketching the graphs first. The keys to sketching any graphs in AP Physics C is going to be pretty simple. There's three parts. The first part is that we just want to think, okay, well, like what are some points that we can have our curve cross through? So that includes, where do we start, like a y-intercept? Where do we end up? Does it ever cross zero? And are there any values that have to be positive or negative, for instance? Second thing would be, once we have a good starting point, is it going to go up the axis or down the axis? Is it going to increase or decrease between intervals or from a certain point that we know or before a certain point? So just knowing if it's increasing or decreasing tells us a lot and is scored for points often on the AP exam. And lastly, we need to know if then the increasing or decreasing is linear or if it's curved. If it's curved, then obviously the way it's bending, is it curving up or curving down? So we call that mathematically, is it concave up? That would be if it's curving up. Or is it concave down, in which case it's going to be curving down. Just to make sure we understand and don't get caught up on this, it does not matter at all what the function is, whether it's some quadratic or whether it's an exponential or a square root function or whatever other kind of power function, or if it's a sinusoidal function that's only part of the up before it goes back down, which is a curving piece. All we care about is the way in which it's curving, not the function. So we don't want to overcomplicate this. Let's take a look at an example here. We're going to be sketching a position time graph on these axes provided to us, and it's giving us a description of the motion here. So it's saying the object is initially moving backwards as it slows to a constant rate. Oh, it slows at a constant rate to rest at time t1. Then it speeds up backwards at a constant rate. So we need to split this into two pieces, before t1 and after t1. So let's start at the beginning. It's initially moving backwards. I don't know where to start here. It doesn't really say anything, but since I'm moving backwards the whole time, it might be good to just start at some point high up the axis to give us room. What's important here, though, is if it's initially moving backwards, that means I can draw an initial slope to be negative, because I know that slope is speed on a position time graph. So I'm going to start with an initial steepness or tilt that's negative because it's initially moving backwards. So it's going to slow at a constant rate to rest. So now I know when it's at t1, it's going to be at rest, which means it's going to have to be flat momentarily. Doesn't matter how high up the axis. I could have made it a little bit lower here, but I want to give myself room for the second part. So I just made it flat right here. And we know since it's slowing down that it should be getting less steep. Again, steepness is speed. So that would mean that we have a curve that is going to be concave up, getting less steep as we go. And then from here, it's going to speed up backwards. And so that means it's going to get steeper with a more and more negative steepness. And so that's going to be a concave down parabola from there. In math, we call when we connect one function or one curve to another, we call that piecewise. To summarize the things that we just needed to apply there is this idea that slope is velocity, right? So we know that the slope is velocity, which means if it's linear shape, it's going to be a constant velocity motion. If it's curved, then it's not a constant velocity, and as we said, steeper is faster and less steep is less fast. It is important to note here that although we don't really care about the curving as a parabola versus anything else, a parabola is going to indicate constant acceleration. So it's speeding up or slowing down when it's constant acceleration. and that would be at an even rate of speed change. You're changing by the same amount of speed each second. The concavity, meaning the way it's curving up or down, is going to tell us the direction of acceleration. So this curved part here is curved upward, and that would mean it's concave up. This part here is curved downward, and that would mean it's concave down. So the first part before T1, the acceleration would point up. After T1, the acceleration would point down and be negative. If we look at a second example here, now this one gives us a graph that's sketched, and it wants us to describe the motion of that shape of curve. So we want to first indicate the time at which it stops. So if I think about this, stopped means its slope is velocity, right? That means we more specifically want the velocity to be 0. So what we're looking at then is where on this curve are there instantaneous flatness? Where is it flat? And so that would be the slope of a tangent line would be 0, and that's in math where we would refer to is those points as being local minimums and maximums. That's an important calculus thing for down the road. And so that would be whatever these values are. We would have 0, 9, and 15 seconds, and that would be the answer to A. In B and C, we're asked about acceleration. So that's going to get in this idea of concavity as revealing the direction of acceleration as positive or negative. So if we're looking at positive first, then I want to be looking for where do we have a concave up parabola. And you can see right here, this is concave up. This is concave down. And then after it crosses 0 here, that is also concave up, and it continues to be concave up the rest of the way. And so these would be the sections of the graph during which we have positive acceleration. If we want to switch over to the negative acceleration, that would be where we have a concave down curve. And that only occurs right here, where we have a concave down. If we're looking at speeding up and slowing down, that's going to go back to slope is velocity. And so in this case, then, I'm looking at speeding up first, and that would mean it needs to be getting steeper so that it's getting faster. It doesn't matter if it's getting steeper negatively or positively, it just needs to be getting steeper. That would be getting faster. So I'm looking for where is it getting steeper. And so you can see here it's getting steeper here. After it crosses 0, it's going to be slowing down. But once it hits 0 and changes direction, now it's going to be speeding up negatively, so it's still speeding up. Now it's slowing down. And then right after this local minimum here, the vertex is going to be then, after that's going to be speeding up. It's going to be getting steeper. For slowing down, now we're looking for when it's getting less steep. And so just as we said before, that's going to be these two sections here where it's getting less steep. If we look at a velocity time graph, and now we want to sketch the velocity time graph for an object that's initially moving forward as it slows at a constant rate, and then changes directions at time t1 and speeds up backwards. There's a lot going on here, so let's figure out where to start. We want to figure out what are some points, like the y-intercept, for example. Since velocity is plotted on my y-axis, the y-intercept is going to be the initial velocity, the initial y value. So if it's initially moving forward, I should plot a positive y value, meaning a positive velocity value. And it says it's going to slow at a constant rate. And it says it's going to change direction at time t1. So at time t1, if it's going to be changing direction, it's going to have to be 0 speed, right? 0 velocity as it changes direction. If it's slowing at a constant rate, I know this has to be a linear decrease to connect these 2 points as opposed to curving. And then after that, it's going to speed up backwards, meaning speed up in the negative direction, and at the same constant rate. So we're going to have the same line before time 1 and the same linear curve, linear trend line after t1. So the same line the whole time, because it's the same constant rate. We have to connect these 2 blue ones, right, with a linear, because it's a constant rate. So a linear trend line, and we're going to continue that same constant rate as it goes to increasingly more and more negative velocities. It's important here to then, if we summarize some of the key ideas, since the y-axis is velocity, then y-axis values or points that we can plot represent the instantaneous velocities at different times. Slope, representing acceleration, can then be either constant velocity, so there is no slope, a flat trend line. It could be constant acceleration, where it's linear, positive or negative. And it could be nonlinear, where it's not a constant acceleration, and that would be where we'd have a curve. So let's check out this last example here of a velocity versus time graph here, where we're going to ask to sketch. And we're going to apply some of these things that we just talked about to this graph. And it's saying that a tennis ball is released from rest from the balcony of a tall apartment building. It experiences air resistance as it falls, which slows its acceleration until time t1 when it reaches a constant speed. So let's again unpack it. Let's start with like, what is the initial velocity? Is it going to be a positive, a negative, or zero? And it says it's released from rest. So we can go ahead and plot the zero. That's our good starting point. So now we can think, is it going to increase or decrease? And we know it's going to be falling, so I'm going to assume that down is negative here. If it's not given to you as being a positive or negative, then you can choose. It won't be a graded thing on the AP exam. They'll let you choose if you want to make this go positive or negative. But the idea here is that it's going to end up at time t1 at a constant speed. So although I know it slows its acceleration, it's going to reach a constant speed. So I'm going to go ahead and just make sure I know that this is going to be a flat trend line because it's a constant velocity after t1. So when I go to connect my initial y-intercept velocity here to my constant flat trend line here, I need to do so with either a straight line or a curved line. Since the acceleration, which is the slope, is slowing with time, then that means it's going to be getting less steep with time. And that means that I would want to connect this with a less and less steep curve, and then flattening out after time t1. And this is our last example where we are now given a graph. This is, of course, is a velocity time graph, and we're going to indicate the times at which the object is stopped. So since we're looking at the y-axis right now, since that's the velocity, and more specifically, we need that to be 0, then we're just going to look for where it crosses 0, y-axis, since velocity is being plotted on our y-axis. If we switch now to looking at the acceleration, we're looking now at slope. This wants a positive acceleration, and so we'll be looking for where you have a positive slope. This is the only time where you have a positive slope, and therefore that's the only time that you have a positive acceleration. If we want the negative acceleration, that is going to also be slope, and we just need where there's a negative slope, and of course that's going to be this first segment of this three-part graph. If now we look at speeding up and slowing down, we have to be actually looking at velocity as being a bigger and bigger absolute value. It doesn't matter if it's positive or negative. Is it getting bigger or is it getting smaller? So speeding up, is it going to be getting y values that are getting further from 0? So with speeding up, we're looking really at the y-axis values, and we're looking for where it's going to be getting further away. So for example, this first part here, it's getting closer to 0. The y values are getting closer and closer to 0, but after 0, it gets further and further away from 0 in the negative direction. So this segment here, after it crosses 0, should be speeding up. And then this part here, again, it's slowing down right here. So it's after it crosses 0, this is going to then be where the values are getting further from 0. So these are the two parts where it's going to be speeding up. We just talked about slowing down, which is again a y-axis, but that's going to be when the y values, since velocity is plotted on the y-axis, are getting closer to v equals 0. In this case, it's going to be that first segment, as we said, and this part before it gets to 0 on the third segment. I hope that this makes sense, and I really appreciate you taking the time to watch this video. Have a good one, and as always, ask questions if you need it.